Hello, everyone. So last time we looked at the concept of increasing, decreasing functions. Increasing, decreasing. Functions and the connection with derivatives. So basically we saw that if derivative of a function is positive on an interval, then the function is increasing on that interval. And if the derivative is negative on an interval, then the function is decreasing on that interval. And we also saw about the concave upward and downward functions. And we saw the connection of this concept with second derivatives. So we saw that if the second derivative is positive, then the function is concave upward, such as x squared, like parabola opening upward. And if the second derivative is negative, then the function is concave downward, such as minus x squared, a parabola opening downward. Let's look at, we did some examples last time. Let's look at one more example. Let f of x equals x plus 2 sine x, because we didn't have time to do an example with a trigonometric function last time. So let's do a trigonometric function this time, x plus 2 sine x, with df, with domain of f, with domain df equals, let's say, 0 to 4 pi. Determine the intervals of increasing, decreasing, and intervals of concave upward, downward. Okay, solution. So we have f of x that is given to us. First, we need to find the derivative to see where it's positive versus negative. That determines increasing, decreasing. And then the second derivative will determine concave upward, downward. So what is f prime of x? F prime of x, derivative of x plus 2 sine x, is 1 plus 2 cos x. So then find or solve for f prime of x equals 0. We need to know the roots of f prime, and based on that, we can draw a sign chart and determine where f prime is positive or negative. So, but first we need the roots of f prime, the solutions of f prime of x equals 0. So that gives 1 plus 2 cos x equals 0, and that gives cos x equals minus 1/2. So what are the solutions of cos x equals minus 1/2 between 0 and 4 pi? Remember, the domain is given as 0 and 4 pi, 0 to 4 pi. So if you want to know the solutions of cos x equals minus 1/2, I suggest you draw the unit circle and try to find out where cos is negative. First of all, try to find out about the quadrants. Which quadrants cos x is negative or cos theta is negative. If you want cos theta to be negative, you can be in the second quadrant or in the third quadrant. So minus 1/2 means here, this length, minus 1/2. And then the angle could be here or here. So pi, well, we know from the table that cos pi over 3 is 1/2. So cos, see, pi minus pi half will be minus 1/2, and cos pi plus pi half equals also minus 1/2. So please remember that from pre-calculus, which we also had a review session in the first lecture, cos pi minus theta is minus cos theta. Cos pi plus theta is also minus cos theta. These are the identities that we can always use. And you can also see it from the picture that cos pi minus theta and cos pi plus theta, if theta itself is in the first quadrant, then cos pi minus theta, pi minus theta will be in the second quadrant, pi plus theta will be in third quadrant, and cos is negative in quadrant 2 and 3. And cos pi minus theta is minus cos theta, cos pi plus theta is also minus cos theta. So in this case, cos pi minus pi over 3 is minus 1/2, cos pi plus pi over 3 is minus 1/2. So what are the solutions of this equation then? So solutions of cos x equals minus 1/2 in the interval 0 to 4 pi are, so let's call the first one theta 1, pi minus pi over 3, theta 2, pi plus pi over 3, see, pi minus pi half, this one second quadrant, pi plus pi half third quadrant. Then we will hit, so we start from here. Remember, this is the positive direction. Counterclockwise is our positive direction. So this is our 0. Then we hit pi minus pi over 3. Then we hit pi plus pi over 3. Then we hit 2 pi. Now, if we continue, because the domain is assumed to be 0 to 4 pi, so we shouldn't end at 2 pi. We still have to continue. So this is 0 and 2 pi. So if we continue, then this is 2 pi, this will be 3 pi, and this angle will be 3 pi minus pi over 3. And this angle here will be also 3 pi plus pi over 3. We know that if we have an angle and we add 2 pi to it, or we add multiple of 2 pi to it, we'll be still in the same location on the unit circle. Therefore, the trigonometric values will be still the same. So this angle is pi minus pi over 3, but if you add 2 pi to it, 2 pi means rotating the full circle once. So it'll be back to the same location here, and cos of the angle will still have the same value. So cos 3 pi minus pi over 3, which is this angle, plus 2 pi, still is, of course, minus 1/2. Similarly, if you add 2 pi to this angle, you'll be at 3 pi plus pi over 3, and still cos value is minus 1/2. So theta 1, I can also call this theta 3 and theta 4. And after theta 4, which is 3 pi plus pi over 3, then we will hit 4 pi, and then that's the end of our domain. So we don't need to continue. But if the domain was, let's say, 0 to 6 pi, then we could still continue one more round. All right, now we can then use the sign chart. So sign chart here, I can specify the x value starts from 0 according to the assumption that says the domain starts from 0. And then I have to write down these roots in the order. The smallest one is pi minus pi over 3, or 2 pi over 3, right? Then the next one is pi plus pi over 3, which is 4 pi over 3. Next one is 8 pi over 3. Next one is 10 pi over 3. And then we have 4 pi. And then we have f prime here and f here. So at these points, f prime is 0. So then I have to figure out about the sign of f prime, whether it's positive or negative. Now between 0 and 2 pi over 3, use a test point. There's a test point here. Maybe I can test point. Let's say I can use x equals pi over 3, for example. Then f prime of pi over 3 will be 1 plus 2 cos x, so 2 cos pi over 3. And this, of course, will be positive. Cos pi over 3 is positive times 2 positive plus 1 positive. So this will be positive. And I don't have any repeated roots, so the signs will change alternately. So positive, then minus, positive, minus, positive. And what about f itself? So this is f prime, where it's positive, where it's negative. So f will be increasing here, decreasing here, increasing here, decreasing here, increasing here. So that's it. So we can say that f is increasing on 0 to 2 pi over 3 and 4 pi over 3 to 8 pi over 3 and 10 pi over 3 to 4 pi. And f is decreasing on which intervals? Between 2 pi over 3 to 4 pi over 3 and 8 pi over 3 to 10 pi over 3. Okay. Now for concavity, we know that we need the second derivative. So we need f double prime of x. F double prime of x means the derivative of first derivative. First derivative is 1 plus 2 cos x. So derivative of this function is minus 2 sine x. Minus 2 sine x. And if I solve for f double prime of x equals 0, that gives minus 2 sine x equals 0. That gives sine x equals 0. And what are the roots of sine x between 0 and 4 pi? So roots or solutions of this equation. What are they? So theta 1 equals 0. Sine is 0 here. Where else? At pi. Where else? At 2 pi, 3 pi, and 4 pi. 0, pi, 2 pi, 3 pi, 4 pi. And then 5 pi, 6 pi, but we don't need them because the domain is only 0 to 4 pi here. And then I can draw the sign chart for f double prime. So x values start from 0, then pi, then 2 pi, 3 pi, 4 pi. F double prime, and then f. So f double prime becomes 0 at these points. 0 here, 0 here, 0 here, 0 here, 0 here. Now between 0 and pi, I can use a test point, such as pi over 2, for example. Theta equals pi over 2, then I can find f double prime of pi over 2. That will be minus 2 sine pi over 2, which is -2, which is negative, right? F double prime of x was -2 sine x. So negative here, positive here, negative here, positive here. So if double prime negative means the function is concave downward, and positive means concave upward, concave downward, concave upward. Well, there you are, that's it. So f is concave upward on which intervals? On pi and 2 pi, and 3 pi and 4 pi. And f is concave downward on 0 and pi, and 2 pi and 3 pi, 2 pi and 3 pi. That's it. So the question was asking about intervals of increasing, decreasing, and intervals of concave up and down, and we found all of them. So let's move on to the next topic, which is relative extrema and graphing polynomials. Relative or local extrema. Graphing polynomials. Okay, so what is a relative or local extremum, or relative maximum, relative minimum? So let's start with the definition. Let f of x be a function with domain df. We say that x equals a is a local or relative maximum for f of x if there exists an open interval containing x equals a as an open interval I containing x equals a, such that f of a is bigger than equal to f of x for every x in I. Similarly, x equals a is called so by the way, this point local max or local min must be always a point of the domain. So I can also mention here that x equals a in the domain belongs to domain is a local Similarly, x equals a, again, of course, in the domain of f is called a local or relative minimum for f of x if, again, there exists an open interval I containing A such that f of A is less than or equal to f of x for every x in I. So let me show you in a picture. Let's look at an example. Consider the following function, or the function f of x with the following graph. Let's say we have a function like this. There you go. Let's say this is, for example, 1. And let's say this is 2, 3, 5. Okay. Find the local max and mean of f of x. So let's start with x equals 1. Well, let me first start with x equals 2. X equals 2. Do you think it's a local max or local mean or neither? So we have to look at the definition. According to the definition, a point is called local max if there exists an open interval containing that point such that f of A is the biggest output among the outputs in that interval. So look at f of 2 here. F of 2 is some value here. We don't know exactly how much because it's not given to us, but this is f of 2. Can I say that f of 2 is the biggest output? It doesn't have to be biggest output in the whole function, and it is not biggest output in the whole function because, for example, f of 5 is bigger, right? But we don't care. We are talking about local maximum or local minimum. Locally, is it maximum? Locally, is it minimum? It is locally maximum because f of 2 is the biggest output, not in the whole domain, but in an open interval. If I consider a small open interval containing 2, then I can say f of 2 is the biggest output among the outputs of that interval. So which interval can I consider here? It should be an open interval containing 2. Why am I saying open interval? Because I want the interval to be around 2 from both sides. If I say, for example, closed interval, then I'm allowed to choose, for example, 2 and 3, which is just one side. It just covers one side of 2, right? But when I say open interval, I cannot say 2 and 3 because then open interval 2 and 3 does not contain 2. My interval must contain the point as well. So can you tell me an open interval containing 2? Which open interval contains 2 here? There are many open intervals containing 2, but we would just want one of them such that f of 2 is the biggest output among all the outputs on that interval. So for example, we could consider, let's say, 1.1, 1.5 to 3.5. So the open, sorry, 2.5. The open interval that we are talking about is a two-sided. It must cover both sides of our number. Because if it just covers one side, then the number itself will not be in the interval, but our requirement in the definition says that open interval I containing A. So the point A must be contained in the interval. So if I say, for example, 1.5 to 2.5, so set so x equals 2 is a local min, since we can set I to be, let's say I can call it I1. I1 to be 1.5 to 2.5, which is an open interval containing x equals 2, and f of 2 is bigger than or equal to f of x for every x in I1. See, if I consider different inputs in I1, for example, this x value, look at f of x. F of x will be this much, and f of 2 is bigger than that. If my x is here, for example, or let's say if my x is here, then again, f of x will be bigger than f of 2 is bigger than f of x. And so on, right? So among all points of the interval 1.5 to 2.5, f of 2 is the biggest output. If x is equal to 2 itself, then of course f of x will be equal to f of 2. And if x is a little bit less than 2 or a little bit more than 2, a number between 1.5 to 2.5, then f of 2 is bigger than f of x. Okay, so f of 2 is the biggest output among all the points of this interval. And this interval is an open interval containing the point. Therefore, we can conclude that x equals 2 is a local maximum. So the points that I have to emphasize and you have to pay attention is that, first of all, the interval must contain the point. So for example, you're not allowed to say 2 and 3 because this interval does not contain the point 2. So the interval must contain the point. The interval must be an open interval. And for local maximum, f of a must be the biggest output among all the points of that interval. For local minimum, f of a must be the smallest output among all points of that interval. Now, based on this type of reasoning, I think you can guess that x equals 3 must be a local minimum. So similarly, x equals 3 is a local minimum for f of x. Set, so can you tell me which open interval I can consider this time? This time, so previous time I considered here 1.5 to 2.5, which contain 2. Now here I can consider which open interval that contains 3, 2.5 to 2.5 to, let's say, 3.5. And f of 3, so 2.5 to 3.5 is an open interval. It contains the point 3. And f of 3 is the smallest output among all the points of this interval. So set I2, the interval I2 has 2.5 to 3.5. Again, this is an open interval. Containing x equals 3. And we can say that f of 3 is less than equal to, this time, f of 3 is less than equal to f of x for every x in I2. So 2 local maximum, 2 is local maximum, 3 is local minimum. What do you think about 1 and 5? So can I say that 1 is local minimum? 1 here is not a local minimum. Why is it not a local minimum? Note, x equals 1 is not a local max or mean, since there is no open interval I such that I is a subset of domain of F and 1 belongs to I. Note that an open interval containing 1 must be of the form, let's say 1 minus epsilon to, let's say 1 plus delta. But no number less than 1 is included in domain of F. See, domain of F starts from 1. But if I want an open interval containing 1, it must start before 1. Because see, I cannot start from 1 itself. If it was a closed interval, then I could start from 1, right? 1 to something, like 1.5, let's say. And this would be an interval containing 1. But because this is supposed to be an open interval, why does it have to be an open interval? According to the definition. Definition requires us to choose an open interval containing the point. So because I want to choose an open interval containing the point, I'm not allowed to start from 1. Because then open interval 1 to some number will not contain 1. So I have to start before 1. I have to start before 1. But no number before 1 is in the domain. Of course, the whole interval that I am going to choose must be entirely inside the domain, right? And I have to start before 1, but no number before 1 is in the domain. So that means no open interval containing 1 is can be chosen that is entirely inside the domain. Therefore, the point here cannot be a local max or mean, because to be a local max or mean, to be eligible to be a local max or mean, you have to be able to choose an interval that is, of course, entirely in the domain and also open interval and also contains the point. But there is no such interval here. Therefore, this point is not a local max or local mean. So similarly, x equals the last point 5 is not a local max or mean, since there is no open interval I such that I is in the domain and I contains 5. There is no open interval in the domain that contains 5. So 5 is also not a local max or min. Yeah. So one remark here, if a point is a local max, local or relative max or mean, then that point is called a local or relative extremum. So in example above, x equals 1, x equals 2, they're both local extremum. Or the plural form is extrema. Extremum is for the single form, plural form extrema. And x equals, so 2 and 3, x equals 2 and 3, not 1 and 2 and 3, local extrema. X equals 1 and x equals 5, not a local extrema. Okay, so another example, let's say f of x equals x squared at x equals 0. See, f of x equals x squared looks like this at x equals 0 is local, minimum or maximum, or neither, do you think? F of x equals x squared at x equals 0 is x equals 0 is a local minimum. Locally, it's minimum. Why is it locally minimum? Because I can find an open interval containing 0, such that f of 0 is the smallest output on that interval. What can I choose as my interval? So set, let's say I equals, for example, let's say minus 0.5 to 0.5. Then f of 0, which is 0, is less than or equal to x squared for every x between minus 0.5 to 0.5. Well, 0 is less than or equal to x squared for every real number x, right? So in particular, of course, we can say that 0 is less than or equal to x squared for every x between minus 0.5 and 0.5. So why did I choose minus 0.5 to 0.5? Because minus 0.5 to 0.5 is an open interval that contains 0. And f of 0 is the smallest output among all the outputs chosen from this interval. Okay, now the question is how to find local extremum. A local extremum means maximum or minimum. For a given function f of x. For a given function y equals f of x. So the answer is in a theorem. A theorem provides the answer for this question. Let f of x be a function such that f of x has a local extremum at some number, let's say x equals a, then we can say that f prime of a is equal to 0, or f prime of a does not exist. So if a function has a local extremum at a point, then the derivative at that point is 0, or derivative at that point does not exist. So look at, for example, the previous example, see, 0 was local minimum. And how much was derivative at 0? The derivative is 2x. At 0 is 2 times 0, which is 0. So this is always the case that if you have a local extremum at a, then f prime is 0 or f prime does not exist. So the very first thing I want you to notice here or pay attention is that the converse of this theorem does not hold. So before saying that, I can say that, for example, an example above, f of x equals x squared has a local min at x equals 0, and f prime of 0 is equal to 2 times 0, which is 0. And now the remark, very important remark, is the converse of theorem above is not valid. Meaning that if x equals a is a point such that f prime of a equals 0, or f prime of a does not exist, then we cannot conclude that f of x must have a local max or min at x equals a. See? There's always, I always say in all math classes, there is always a difference between a statement and the converse of a statement. I also gave you this example, I think last lecture or maybe one lecture before that, that if it's a Monday, let's say I have classes in college on Mondays and Thursdays. If it's a Monday, then I go to the college. So this is true. What is the converse? The converse reads as if I go to the college, then it must be a Monday. That's not true because it could be a Thursday. So a statement, if a statement is valid or true, it doesn't mean that the converse is true. So here we are saying that if A is a local max or min, then f prime is 0 or f prime does not exist. But the converse is not true. If f prime is 0, f prime does not exist at some point, then we cannot conclude f must have a local max or min at that point. Meaning that even if f prime is 0 or f prime does not exist at some point a, then the function may or may not have a local max or min at that point. So an example verifying this is consider f of x equals x cubed at x equals 0. See, this is how the graph looks like at x equals 0. This is neither x equals 0 is neither local max nor local min. Neither local max nor local min, although f prime of 0 is 3 times 0 squared, which is 0. See, x equals 0 is not local max because there is no open interval containing 0 that f of 0 is the biggest one on that open interval. See, we said that always open interval containing a point is a two-sided interval. It must cover both sides of the point. So if I consider an open interval both sides of my point 0, such as this, then no matter how I choose my interval, as long as it covers both sides of the 0, f of 0 cannot be the biggest point of this interval because there are some points to the right of 0. For example, look at this output. This output is bigger than f of 0, which is 0. So f of 0 cannot be the biggest one. Similarly, f of 0 cannot be the smallest one because there's always some points to the left of 0, such as this point, where f of 0 is bigger than this, right? So f of 0 cannot be the smallest one either. So there is always, no matter how you choose your open interval around 0, f of 0 will not be the biggest one output and will not be the smallest output. So that means x equals 0 is neither local max nor local min. But f prime of 0 is 0 here because f of x is x cubed. So f prime of x is 3x squared and f prime of 0 will be 0. So this example shows that, see, f prime of 0 is 0, but 0 is neither local max nor local min. So even if f prime of a is 0 at some point a, or even if f prime of a does not exist for some point a, then still we cannot conclude that f must have a local max or min at that point. It may have, but it may not have. So how is that? So if we cannot, if from f prime of a equals 0, we cannot conclude that the function must have a local max or min, then how is that theorem helpful? Because it would have been nice if we could conclude from this, if from this we could conclude f has a local max or min at that point a, then everything would have been very straightforward and easy. But that's not the case. So how can we apply this theorem in practice? So I'm going to explain this to you, but first let me tell you a definition, because this criteria is important for us, that f prime is 0 or f prime does not exist. So we are going to give it a name. So definition, let f of x be a function let f of x be a function with x equals a in domain of f. We say that x equals a is a critical point we say that if x equals a is a critical point for f of x if f prime of a is equal to 0 or f prime of a does not exist. So critical point means a point where f prime is 0 or f prime does not exist. So let's say this is part A of the definition. Part B, we say that x equals a is a stationary point for f of x if f prime of a is equal to 0. If f prime of a exists and is 0. So each stationary point is a critical point. Right? Critical point is defined as a point where f prime is 0 or f prime does not exist. Now this f prime 0 itself, we are giving it a name. If f prime is 0 at some point, we are calling it stationary point. So critical point means either a stationary point or a point where f prime does not exist. Therefore, I can say that if a point is stationary, then it's critical point automatically. But if a point is critical point, then it may be stationary point or it may be a point where f prime does not exist there. So critical point is usually appear more frequently in different texts and different examples. So please pay attention mostly to critical points, but I just wanted to mention the definition of stationary point so that you hear this as well, but pay more attention to critical points. Critical point of a function means a point of the domain where f prime is 0 there or f prime does not exist there. So based on this definition, the theorem above says what? Because the theorem said if a function has a local extremum at x equals a, then f prime of a is 0 or f prime of a does not exist. But I'm calling this f prime 0 or f prime doesn't exist. I'm calling such a point as a critical point. So if I combine this theorem with the definition I just mentioned, I can say that if a function has a local extremum at a, then that point A must be a critical point. So therefore, theorem above states that if a function f of x has a local extremum at some x equals a, then x equals a must be a critical point for f of x. Again, but not conversely. Meaning that if x equals a is a critical point. Then if x equals a is a critical point, then x equals a may or may not be a local extremum. Okay, so the converse is not true. If you have a critical point, then it may or may not be a local extremum. But if you have a local extremum, then for sure that local extremum must be a critical point. And how can I explain this? So let's say I can compare this with, let's say, hiring instructors, let's say in the college. Let's say college wants to hire a good instructor, right? So a good instructor, how can they choose a good instructor? First they can look at the resumes, right? So a good instructor, of course, has a good education or high education, right? So they can say, okay, we will look at the list. If the person has a high education, then potentially he or she can be a good instructor. So they will choose, they look at the list, among the list or resumes or CVs that they have received, they choose the ones with good or high education. So these provide the list of potential good instructors, but having high education does not automatically mean or imply that being a good instructor, because maybe the person has high education or maybe even lots of papers, but they don't have the good or enough teaching skills, right? So list of people with high or good education provides a list with potential good instructors. But then each of those persons may or may not be a good instructor. So in other words, if a person is a good instructor, then they must have a high education. But if a person has a high education, then they may or may not be a good instructor. So same thing here. If a point is local extremum, then it must be a critical point. But if it's a critical point, then it may or may not be a local extremum. So how can I use this in practice then? So given a function f of x, if we find all critical points, the set of all critical points, it provides a list of potential local extremum although no guarantee that each of those points is a local extremum. Okay, so it is useful. So it is useful to know which candidates among the people who submitted their resume, which one of them or which ones of them have high education, because once we choose people with high education, that provides a list of potential good instructors. But then we have to look at them one by one to see each of those, whether they're actually good instructor, they have good teaching skills or no. Same thing here. So first we need to, so the theorem is useful. It helps us to find a list of potential local extremums, but then we have to look at them one by one and see whether each of those is actually a local extremum or no. Okay, guys.